Fantastic. So what we did is that we used the deltas of the output layer to find the deltas of the previous layer. And using the deltas, we updated the weight. So today's class is going to be the continuation of the previous class. In the previous class, where we stopped was, so what we found out is that, so we had two layer neurons, neuron A and neuron C. So they were connected like this. So the change in outcome in neuron C is given by AM into AC, and whereas the change in the network is given by CM into C delta. So what we did is that we combined both the things and then we wrote a new equation where change in the network is given, change in the error network is given by AM into AC into C delta. So we combined these two and then we found A delta. A delta is nothing but AC into C delta. So we literally skipped the C neuron from the picture and then we calculated the total error contribution from AM. So AM is equal to AC into C delta is EM. So this is AM into A delta is equal to EM, in other words. So we did a simple math and we found out this one. But in our actual neural network, if you look at it, we had A, B, C, D. The outcome of neuron is not just going only to the C, but to D. So one more part is missing. Initially, we assumed only A and C connection, but now we assume this connection also. The output of A is shared by D also. So how can we visualize this?
AD into D delta, madam.
Fantastic. So I will pictorially draw that one. So if you look at it, so this was previously figured. So similarly, the connection between AD can be established as AM into AD into D delta is going to give the change in error due to this connection. So ultimately, so initially we wrote A delta is nothing but AC into C delta. But we have another connection also, which is due to AD. So A delta can be written as like this. Is it clear? Sorry, D delta. Is this portion clear?
Yes, ma'am.
So if you look at it, there are two change in errors. One due to the connection between A and C and another due to the connection between A and D. So the total change in error is nothing but the summation of both errors. When the output of neuron A is used by both C and D, the resulting changes of the error will add together. So previously, if the error was this much, this is change in error from AC. This is change in error from AD. So this is EM into AC. This is EM into AD. So the new error will be this much. So this will subtract from the previous one and this will subtract from the previous one and then you will get a new error as a resulting change. After adding the error changes due to this one, you will get the remaining change. So every error will get accumulated. How we are accumulating A delta? Similarly, we are accumulating the errors due to individual connections and then we remove it from the a new error. Is it clear? So even if you have one more neuron, one more term will be added to the A delta. We saw it for one connection. We need to extend it for the multiple connections and then add the term to the delta value. So similarly, if this is the case, what will be the B delta value? B delta value will be BC into C delta plus BD into D delta. So this is the value for B delta. However, how we did for A, we have to do it for neuron B also, and we will get the similar value like this. So like this, we can get the value of delta for every neuron in the network. It doesn't matter how many layers it has, how many neurons it has. The same procedure we will follow, and we will get that. Is it clear?
Yes. Yes, ma'am.
Oh, so now we will see some of the conventions. So if you have a neuron A, an arrow mark tending towards the right shows it is an outcome. An arrow mark tending towards the left shows it's a delta value. So if you have two neurons, A and C, both are connected with the weight AC, then if you are going from left to right, then this indicates a multiplication between A naught into AC. For the same neuron sharing the same weight, if you are looking from right to left, then this is AC multiplied by A delta. Sorry, C delta. Because you are going from this direction to this direction. So you are multiplying C delta to this one. So if you look at, so if you remember these conventions, we can see how the backpropagation algorithm works. So let us imagine one neuron H. So what this neuron does, so it collects some of weighted input values from the other neurons. Let's say we have three neuron outputs, A naught, B naught, C naught. This be the weight between them, AH, BH, CH. So you get an output called H naught. So H naught is nothing but A naught into AH plus B naught into BH plus C naught into CH. So this is in the forward pass. In the reverse pass, so what I said in the reverse, we get delta value. So let's say we have three neurons, J, K, and L. So J delta, K delta, L delta. So these values are same H. So HJ, HK, HL. So all these three values get multiplied with the weights and we get the H delta value. So H delta value is nothing but multiplication of these weights with the delta value and summation of all these incoming delta values. So this is the H delta value. So if you look at it, it reveals some important practical result. So if the number of neurons connected is same as if the preceding number of neurons is same as the following number of neurons, then the amount of work taken to compute the H naught is same as the amount of work taken to compute H delta. So this will differ only in the output case because the number of it does not has the next layer to calculate the delta. So the output layer we need to treat it as a special case. So the process of finding delta for every neuron in the network is called as a backpropagation algorithm. So now let's see in action. So let us assume we have a new network. Let this network has two inputs, two input features X and Y, and it has got three hidden layers with two neurons, four neurons, three neurons, and the output neuron is two. So it has two inputs, two outputs, P1 and P2, three hidden networks. So this is a new classifier with two input, two output, and three hidden network. We start off evaluating a sample. We provide the values X and Y features to the input. Eventually, it will produce the output with the prediction P1 or P2. So when we start the back propagation algorithm, what we will do? We will start off with the final layer. So we will compute the error. Then what we will do after computing the error, we will find the delta value for one of the neuron. Then we will find the delta value for the another neuron. Then what using this one? So using these two delta values, this P1 delta value and P2 delta value, we will compute the delta values for this neuron, this neuron, this neuron. So after finding the delta values for this one, what we will do? We will use only these deltas. We will forget about these deltas. We will use only these deltas. This delta value will be used to find, so this neuron will use delta values from these three neurons. This delta will use delta values from these three neurons. This one will use from these three. This one will use from these three. Similarly, for this one, we are only concerned about the deltas from this layer. So this one will use deltas from these four neurons. This one will use deltas from these four neurons. So in this way, we will calculate all the neurons from the back to the, sorry, we will calculate all the deltas from the, starting from the back layer to the input layer. So what we are doing, this is called as back propagation because the deltas from any layer are propagating and moving their information backward one layer at a time and modifying it modifying it as we go. So if you have seen this, the computing here is very fast because it takes only one multiplication and addition. So, uh, it does in no time. And if you use GPU like parallel hardware, then the efficiency becomes much more faster. So because here the tremendous efficiency comes from parallelism because parallelly we are at the same time we can compute the deltas for all the neurons in the same layer. So this is called parallelism, and this adds efficiency to the backpropagation algorithm. So we have all the deltas. Now we have all the deltas in the network, and now we can update the weights. So we can actually do the weight update. Once we updated our weight, then what we need to do is that we need to recompute the deltas because our weights are based on the deltas. So once computing the weight, we have to recompute the deltas. So this comes to a conclusion of the backpropagation algorithm. There is only one more small thing left out. What is that is using activation functions. So including activation function in the backpropagation is a small step. So far, we have ignored the activation function. We didn't consider the activation function is present, but including them into this one is a small step. But understanding that small step needs a little bit of thinking. So we will start off thinking a neuron. We will take a neuron. Let this neuron use an activation function. So it in the feed forward connection, it gets the input from the previous layer, it gets added up, and then it is passed on to the activation function. After the activation function, we get the output. Let's imagine that we have a sigmoid function. If you look at the sigmoid function, so after minus pi, it is close to 0. After plus pi, this value is close to 1. Between minus pi to plus pi, the values are like an S-shaped curve. They are blended smoothly. So that's the name. It has got the name called sigmoid. So this is a sigmoid function. So if you look at the neuron C in our original thing, let us assume now only this connection. For time being, we will ignore B and D. We will assume only this connection in our neural network. So what will happen when we have an activation function? So when we have an activation function in the A, so what will happen? Outcome of A, this is outcome of A is A naught, and this is multiplied by a weight called AC, and then it goes into the activation layer. The activation layer, here we have got A naught into AC.
This is a C neuron, am I right, ma'am?
Yeah, this is neuron C. Because already we are out of A naught. We are just looking at neuron C. So the outcome of this one is C naught. So now if you look at it, we will use the activation function. This is input, this is output. So this output will correspond to C naught. So this is how activation function is used, and then we will get the output. This is normal. Suppose we are changing the weight. Then let us assume that, let me draw here, A naught into AC plus ACM. We are adding a weight to AC. So then what will happen? There will happen a shift in the computed value. Then this will shift in the activation, and this will provide a larger C naught, and thereby there will be changes in the error also, bigger changes in the error. Imagine if the weight is going to be in the shallower part, then C naught is going to be little. The changes in the network error also little. When the weight is larger, when a larger weight is added, C naught changes is also larger. This shift is happening because of the activation function. So this activation function, if it happens to be, if the input is happen to be strike in the shallow layer, we will get lesser values. If it is in the steeper part of the activation function, we will get larger values of C naught. Thereby, the change in error will be also larger because they are proportional. So if you look at it, we would like to have something to tell us that for any point on the activation function, we would like to know how steep the curve is. So how can we get to know this one? So suppose when we are at the point where the curve is going up steeply to the right, then positive changes in the input will get amplified a lot. Suppose if the point is in the shallow point to the right, then the changes will be amplified a little. So the best way of knowing this one is through knowing the slope of the curve, that is the derivative. So for the sigmoid, function, the derivative will be like this. So this is 0, this is 0, this is 1, and this is 0.2. So when the curve is flat, the derivative, the curve is flat, the slope is 0. When the slope is 0, the derivative is 0. So the derivative is 0. When during the transition part, there is a slope. So corresponding to the slope, there is an increase and then there is a decrease because after this, the slope becomes 0. Here it gets saturated at 1. So the slope again comes to 0. So this derivative will tell us how steeper our curve is. When we are on the steeper part of the curve, we want to increase the value of the delta for the neuron because the changes to the input will cause big changes to the activation function, and thus we will have big changes to the network error. But when we are on the shallow part of the curve, the changes will have little effect to the changes in the output. So we want to make the neuron delta as smaller as possible. So how do we incorporate this into our activation function? So we saw what happens in the activation function during the forward pass. So during the backward pass, how this activation function is involved is, I will see it in a minute. So previously we saw here what happens in neuron H. So we get the input from the previous layer, it gets multiplied by the weight, and all these things are added up, and that we get it as a output H naught. And then in the backward pass, what happens? The delta from the previous layer gets multiplied with the corresponding weights, and then they are added up together, and we will get that as H delta. So this is while we are ignoring the activation function. Now we are including the activation function. So what happens? So after adding a, let us assume the output of this one is Z. So we will look the Z into the activation function, and this is falling here. So the corresponding output will be H naught from this activation function. So meanwhile, we will take the Z. We will look the steep of the curve through using the derivative of the activation function. We will take the for the same activation function, we'll take the derivative. In the derivative, we will look our Z and we will find out our H delta. This H delta will get multiplied with the previous H delta, which is coming out from here, and that will act as our H delta for that neuron. So this is how activation function is incorporated into the neuron in the backward pass. So if you look into it, during the forward pass, what we need the outputs from the previous layer and the weights from the connection between them. We need only these two to find out the H naught. Here, what else we need? We need the deltas from the preceding layer, and we need the following layers and the weight that is connecting between them, and the derivative of the activation function is needed because it gets multiplied with it. So that thereby, whether the diminishing effect or amplifying effect, it gets incorporated into the delta. So based on here how the network error changes, so the same impact it will produce by multiplying its derivative with this one. So that will get incorporated in the H delta. So what we can do is that so far we have assumed something, we have ignored it. So instead of ignoring that one, what we can think is that we would have used an activation function which has an identity function. So what is an identity function? An identity function is nothing but whatever is there as the input, we will get the same as the output. So the derivative of the identity function is 1.
Y is equal to X, ma'am, identity function.
Yeah, y is equal to x. So why we have derivative is equal to 1 means derivative is nothing but the slope of the curve. The slope of an identity function is 1. So the derivative is going to be 1. So if you look at here, if you are using this one, so whatever is the input, we are going to get the same output. So there is no effect in the forward, sorry, here. So whatever is the input is going to be the output if you use the derivative function. So there is no use of the activation function in the forward pass. Similarly, the derivative is going to be 1. So whatever multiplied with 1 is no change. Whatever is this one, the same thing we are going to get. So here our activation function is identity function. So during the forward pass, the output would be unchanged by this function. It has no effect. Yeah.
Activation function for a sigmoid curve, the slope is not 1,
Yeah.
no, madam.
No.
For
That
sigmoid
is
curve, you're
different.
saying this. Uh,
This I'm explaining for because previously we ignored the activation function. So I'm
okay.
saying instead of ignoring it, we can consider that we have used an identity function as an activation function.
So no changes.
No changes. So we can also use any of the other activation function. For example, we can use ReLU also. If you use ReLU, so what is ReLU? Till 0, the output is going to be 0. After 0, whatever is the input, we will get that as an output. That is ReLU function. So the derivative of ReLU would be, so till 0, it is 0. The slope is constant, so we get a 0 function. After that, the slope is or input is going to be output. Slope is going to be 1. When slope is going to be 1, we'll get the derivative of 1. So this is, so there is a jump at the point of 0. There is a jump between from 0 to 1. So that will be managed by the libraries to have a smooth derivative everywhere. It will be managed by the libraries. So we can, everything we did with sigmoid can be applied to ReLU also without a change. And the same goes for any other activation function.
So the
So
ReLU up to 0, it's like the derivative is 0 because the slope is 0. But immediately it shifts to identity function, right?
similar, yeah, it shifts to identity function. Then not identity function, the slope is 1.
Slope is 1, that's what. Identity.
Yeah. Identity function, the slope
In
is
in
1
the
for
in
everywhere, but
between
here only partly it is. Yeah.
in between that identity function home is a straight line. From 0, it will immediately go into that flat
Yeah,
line, or
there is a sudden jump here.
so it should be a perpendicular line, no, madam. So it should be
So what?
perpendicular.
No,
Rail,
no. So I
uh,
have included here a filled 0 and here
yeah,
a
got it, got it.
unfilled dot.
Yeah,
So that
yeah,
means
got it.
this is not, this point is not included, this point is included. They are not continuous.
Sure, ma'am. Okay.
Okay. So this is how we are including an activation function into the backpropagation algorithm. So now let's look into the last part of it. So we will look into the critical control that keeps everything working well. That's the learning rate. So suppose if we are changing the weight a lot, then this is definitely a trouble. Suppose if you are changing the weight very little, then what will happen? We can't change the weight a lot in a single step. So that will lead to trouble. Similarly, we cannot change the weight very little. Why? Because our learning will be very slow. So we need to control the amount of change to the weight during every weight update. So that is using an hyperparameter called learning rate. So what is learning rate? It controls the amount of change to the weights during every update. So it is a hyperparameter. Hyperparameter means the value which we set. So it is given by the letter called eta. This value varies between 0 to 1. Imagine if you set the value as 0. If the learning rate is set as 0, what will happen? The weights won't change. They will never change and there will be no learning. Suppose if you set the learning rate as 1, what will happen? They will overshoot the mark. The system will change, there will be big changes to the weight. And might overshoot the mark. So we usually set the learning rate between 1 to 2, sorry, 0 to 1. Between the extremes, we have to set the rate. So previously we saw the weight update with this one, with the pictorial representation. Now we will see with the learning rate how we can do that one. So we have two neurons, A and C. So C delta is coming this way, A naught is coming this way. So what we will do, we will multiply A naught and C delta, and this will get multiplied by -1. So this is minus A naught into C delta. So this gets multiplied by the term eta. This here we have the term AC. So we added to this term. So we have AC minus eta into C delta. So this is how we update. Initially we were straight away subtracting this from the weight. So now what we are doing, we are scaling it at the value called eta. So this is the learning rate. This helps us control how fast our network learns. So by controlling the amount of weight, it changes during every update. So suppose if eta value is very small, say eta is going to be 0.01, then each change will be very small. So the network will be learning slowly. So it all depends on the choice of the learning rate. So the best choice of the learning rate is dependent on the specific network we have built and the data which we are training. So we have to choose the best learning rate. There are algorithms which automatically give the starting learning rate, and also there are algorithms to fine tune the learning rate automatically. They are called as learning rate schedulers. So they will itself automatically pick which learning rate is good for your network. There is libraries for that one. So if we do not know which learning rate to set, then what we will do is that we will start off by setting the learning rate as 0.01, train for a while, and then later shift our learning rate based on the learning. We can shift whether we can increase or we can lower it, and then we can train again. So this is how we hunt for this. It is usually using trial and error method. We fix the learning rate. So With this, we conclude the back propagations. So in back propagation, what we did is that we started off with a sample, we send it to the network, and then what we did, we calculated the output for a neuron. And then we started the back propagation algorithm. What we did, we computed the delta for the output neuron. And then we had a formula for the change in the network error is equal to change in the output times the delta value. So now after learning this one, what we did, we took a step backward and we found out the previous layers delta values. And then what we did, we continued this one and we then computed all the deltas. So for doing this, we needed only the delta from the output layer and the weights between the two layers. We didn't need anything else. We used the weights and the delta from the previous layer. So once all the deltas were assigned, we updated the weights. So using the delta and the neurons output, we computed the adjustment to every weight. So then what we did after doing this one, we scaled the adjustment by learning rate. And then we added it with the current value of the weight. Get the new weight. So this is the process we learned in the back propagation. So with this, we conclude the back propagation and also we conclude the class for this semester. So if you have any questions, please let me know.
That's it for the semester, ma'am.
Yeah, till April we have classes.
Okay.
So we will continue this one in the next course where we have a course called Understanding the Data. So we will continue some of the portions in this class to the next semester.
So next semester will be understanding. It's deep learning or it's something different, ma'am?
No, it will have portions of deep learning also, but we will learn data science only.
Data science. Okay, ma'am.
So do you have any questions in back propagation or any of the things in this current course? Please let me know. So were you able to understand, appreciate what is being dealt in the class?
Yes, ma'am. Definitely yes.
Yes, ma'am.
Initially, it was little thing, but as the class progressed, man, I could be able to make it out. I can understand things better.
That's very
So,
nice to hear.
I mean, I also did study it. I mean, every time I go home and next day I used to ask Srinath and download the video and do some revision. So it was really useful, ma'am. So
Oh,
thanks for the mentorship.
my pleasure.
Uh,
So for others, how was it, Varshini?
Ma'am, the post was very helpful, ma'am. Like sir said from starting, like every day we started understanding it better and better. Now we are having one like better idea what how things work and all, ma'am.
Okay, very
So
nice to
thank you,
hear
ma'am.
that.
The class was very nice, ma'am. Like it, you made it so simpler for all the doctors to understand. Even if we don't have a background in this, we were able to understand everything.
Thank you. It is so nice to
there's
hear.
a
So if
concept called ELIF. There's a concept called ELIF. Explain like I am five. I mean, explain like I am 5 years old.
okay.
That's, I mean, Reddit and all will be there. So we made it as simple as the thing so that I can understand. Because when I referred the technical, I mean, papers, I think it will be very technical. And I understand
Hmm.
this derivative. I mean, when I went through the BAP propagation, derivative and chain rule of calculus is very important, and at least the derivatives and slopes. I mean, I'm parallelly learning my math, revisiting my mathematical subjects as well.
Oh, very
So
nice to
max
hear, sir.
is very fundamental to understand the center. I mean, initially I had that statistics was more important for data science. I mean, for deep learning, but at one point of time I realized it's more for data science than for deep learning. And so many years I was, banking on statistics. But of late I started to read vectors, matrices, and calculus and derivatives.
Very nice, sir. Keep learning. So that
Yeah,
is
yeah.
how
I mean, learning is my passion, ma'am. It's not like that I do it for just for this degree, but I really wanted to understand the things and concepts so that when I wanted to apply it, I will. And application will be very useful for me. I mean, it's not just apply something, and it's a great learning.
sure, sir. If you have, when you go through it, if you have any doubts, please let me know.
Yeah, yeah. I'll be troubling you for my this work. I mean, my project work. So I'll be asking you. I mean, I mean, related to my projects, and I have plenty of doubts. I'll be
Even I,
keeping.
it was a good learning experience for me also because this was a different medium for teaching. I should thank you all for giving me this opportunity. And I should also thank Professor Krishna Kumar. He shared a lot of resources for teaching this course. So I'm very
Oh,
happy to hear from you all like this. So I hope you benefit from this course. So one more thing to add, on 11th of May, we have a presentation. So that will be taken for your final evaluation. So please be there on 11th of March, sorry,
sure,
11th of May. So that is from 10 o'clock to 1 o'clock. So there will be a presentation. You have to present your project. So we will evaluate. So already the evaluation criteria are discussed in the class. So based on that, there will be evaluation, and that will be taken for your final grades.
sure, definitely.
Ma'am,
Okay.
what about the report, ma'am? How to send the report to you, ma'am?
You can email me.
Okay, ma'am.
You can email, or on the final day, you can bring it as a hard copy. Any ways is fine.
Okay, ma'am.
Okay then.
When is the next semester
Thank
commences? When is it?
August.
Okay, okay.
Okay, sir. Yeah.
Thank you,
Thank you very much.
thank you, thanks,
Thank you.
thanks.
Thank you, ma'am.